Hello, my name is London Dunham, and I am the inventor of the magnetic acceleration propulsion system. And this first one that I'm showing you is the London spinal assemblage. And what that is, it's a culmination of the London assemblage, which is three magnets, and then combining those three magnets with another set of three magnets, and then combining those two sets of magnets with another set of magnets. And that's called the London spinal assemblage, LSA. Now, what's going on is I get three different magnetic strips per se and polarity orientations when I do that. You get the top one, you get the bottom one, and then you get the middle one. And it's on both sides of the LSA casing. So I got the top one. There's a row of the systems all the way down. Now, this right here, what I got in my hand is the LPS, which is a linear polarity switching series. And it's nothing but a bunch of magnets. In this case, it's like maybe 18 magnets inside that one casing, the LPS casing. And they're just regular permanent magnets, but they're in series, connected at their the points of attraction. The cart I'm going to put it on, as you can see, it's friction. It's a strong friction to it. But once we put the LSAs on top of the cart, you'll be able to see it actually overcome that friction. So right now, the LSAs are being put on top of the cart. The cart now is being put, and then there's guideways that the wheels be on, and it's being put on next to the LPS. And you see it go. It goes slow. I don't have it going too fast because it's a small little prototype here. But as you can see, it goes and then it stops. Well, exactly where I said it would stop at. So if you want to see it go further, you have to put another LPS on the other side and stagger it. And then as you can see, it'll make it go even further than that. So putting those two combined together, you'll actually see it switching from one LPS to the other LPS. So that's what you see here. It's going from the first LPS, and then now it's switching. It's going to the other LPS now. And it's continuous drive. And that's basically what the whole system is right there. It's like a switching mechanism that's embedded within the permanent magnets. The and how it's working is it's going from one LPS series, and then on the other side of the cart is the other LSAs, and they're attaching the other LPS system. So the permanent magnets are actually what's making it drive and go and pretty much be better than the friction that's holding it. Now, if you want to go a little faster, you want to go just a little bit more faster. Like I said, there are two lobes here. The one that we have right now set is on the middle lobe. Now I'm going to add the top lobe to it now. So we'll have two lobes, and you'll see the first one goes faster, and then in which case the second one, it'll slow back down again because I'm only dealing with just the one middle lobe, and that's it. Now, Bertha is same set of magnets, same series of magnets. It's a LPS, but it's just LPS with more force. So we should get more force going against the LSAs. So by adding more force, it should have more strength, more acceleration, and a strong acceleration actually. And to see it continue to go at that pace and at that speed, you add again. I only got Bertha on one side of the LPS, so if I put it on the other side of the LPS, you'll see it in staggering. It just keep on going all the way through. I made this whole thing because I really, really wanted to see our whole infrastructure go to a different phase. The system itself does not use no fuel. It does not use any electricity. There's no electromagnetism. There is no superconductors like the maglev systems. And as you see, when it's switching from LPS to LPS, the switching is automatic, so there's no computer that would lag on it. There's no switching component that's needed on there because it's all embedded inside the permanent magnets. You see it in staggering. It just keep on going all the way through. I made this whole thing because I really, really wanted to see our whole infrastructure go to a different phase. The system itself does not use no fuel. It does not use any electricity. There's no electromagnetism. There is no superconductors like the maglev systems. And as you see, when it's switching from LPS to LPS, the switching is automatic, so there's no computer that would lag on it. There's no switching component that's needed on there because it's all embedded inside the permanent magnets. Now, the benefits behind this, because it is able to be attached to anything with wheels, and such as like a train. The benefit behind that is we don't have to design a whole new train station. We don't have to design a whole new layer of tracks for it. The system itself can be retrofitted onto the bottom of the existing trains or anything that's existing, like in a warehouse setting that has wheels on it. Anything that's presently going around with the wheels, this can just be put in place and retrofitted in and replace the engine part of it. The part that it makes it accelerate, and the part that makes it decelerate, and the part that makes it stop and slow down. So it's a great benefit, and to be truthful with you, it's one that will help our infrastructure out right now. And it's not too expensive because there's no fuel that needs to be paid constantly, every week, every month. There's no electricity that needs to be paid for every week, every day. Once the system is installed, it pays for itself, and then the revenue behind it, well, I guess we have to see. It's going to be way past what we can imagine. All right, again, thank you, and that's the magnetic acceleration propulsion system, MAG-AC propulsion system for short. Let's help.